Right now, one of the biggest challenges for SpaceX and NASA is that Starship may need around 10 launches just to refuel in orbit before it can head anywhere beyond Earth orbit. So there has to be a better way. And there is. This is the idea of a nuclear-powered Starship, and it could make getting to the moon this decade a whole lot easier. The problem with how we're doing things right now is we're kind of hitting the ceiling of what's possible. The Raptor engine from SpaceX is state-of-the-art, but it also shows the harsh reality of what traditional chemical rockets can really do. Meanwhile, nuclear thermal rockets are on a whole different level. Their efficiency can be up to 3 times higher than chemical rockets. They can still produce similar thrust, and they could even run on a range of propellants like CO2 or ammonia. That means faster trips, bigger payloads, and way more flexibility in space. And most importantly, nuclear propulsion could cut down the need for orbital refueling, meaning you don't have to deal with things like propellant boil-off or the risk from micrometeorites and orbital debris. So, what would it actually take to turn Starship into a nuclear-powered spacecraft?
Let's get one thing straight. A nuclear engine won't launch a rocket from Earth's surface. The risk is simply too high. If a rocket carrying an active nuclear reactor were to explode on the launch pad, it could lead to a disaster on the scale of Chernobyl. Instead, the plan would be to use a conventional chemical rocket to carry the nuclear-powered spacecraft into orbit. Only once safely in space would the nuclear reactor be activated. These reactors could provide a tremendous amount of energy, not only to drastically cut travel time to destinations like Mars, but also to support long-term human outposts on the Moon and beyond. It's estimated that the most effective setup for a nuclear-powered Starship would use a methane-fueled engine with a power density of 1,000 kilowatts per kilogram. One of the key advantages of using liquid methane instead of something like liquid hydrogen is its higher density. That means you can carry a lot more propellant in the same tank volume. And more importantly, you don't need to redesign the existing Starship tanks. The same tanks that work for chemical propulsion can work for methane-fed nuclear engines too, which simplifies things. Of course, this doesn't mean you can just slap a nuclear engine onto Starship and call it a day. There are real challenges to work through. The nuclear version would still be the same 50-meter-tall steel vehicle launched by the Super Heavy booster. It would still rely on vacuum-optimized engines for space travel, smaller gimbaled engines for landing, and those large flaps to manage re-entry. But one big issue is radiation. Since this version of Starship would be crewed, shielding becomes a critical design priority. The problem is that the ship's shape isn't ideal for protecting people from a nuclear engine's radiation. Those big flaps, for example, could reflect radiation back toward the crew cabin at the top of the vehicle. It makes sense to retract them during engine burns to minimize that risk. Radiation that can't be avoided has to be blocked using something called shadow shielding. These are layers of different materials placed as close to the reactor or engine as possible, designed to absorb different types of radiation and create a protective shadow zone where the crew sits. It's not perfect, but it's how we manage the risk. In terms of performance, the numbers are impressive. A nuclear methane engine with 1,000 kilowatts per kilogram power density could reach a specific impulse of around 625 seconds. Each engine would deliver about 2,610 kilonewtons of thrust, while outputting 8 gigawatts of power. With its radiation shielding included, one engine would weigh about 8.4 tons. A set of 3 would produce 7,828 kilonewtons of thrust and weigh roughly 24 tons combined. The standard methane tank holds 617 tons of propellant, and with an expanded landing reserve of 36 tons, the total initial mass of the nuclear Starship comes out to about 891.3 tons. From that, you get a delta V of 7,209 meters per second, which is finally higher than what the original chemical Starship could manage. Add in the 3,944 meters per second provided by the Super Heavy booster during launch, and you get a total of 11,153 meters per second, a huge improvement. This opens up 2 exciting possibilities. One is increasing the payload. If you scale the engine thrust up to 9,128 kilonewtons, even though the engine mass increases to 29 tons, you could lift 245 tons of payload into orbit. That's more than double the current capacity. As a result, you'd only need 3 refueling flights to prep a Starship in low Earth orbit instead of 12, which makes the whole system much more efficient and less risky. The other option is to go lighter. You don't have to fill the tanks all the way for every mission. For something like a lunar trip, the Starship could carry just 323 tons of propellant, almost half the tank, and still perform a complete orbital mission with around 9,200 meters per second of delta-v. So lunar missions will definitely become much easier. The original chemical Starship HLS was capable of carrying around 100 tons, maybe a bit more, from low Earth orbit to the Moon and landing it there. But there was a catch. It couldn't come back. Once it was on the lunar surface, that was the end of the mission for that vehicle. Now, if it carried no payload, it could technically make the round trip, go to the Moon, land, and return to low Earth orbit. But that's not particularly useful. A vehicle that only works without a payload isn't doing much for exploration or logistics. Now compare that to the methane nuclear Starship. In a one-way mission to the Moon, it could deliver up to 271 tons of payload, assuming it could land using its nuclear engines. But here's where it gets really interesting. The nuclear Starship could actually perform a full round-trip mission, fly from Earth orbit to the Moon, land, unload its payload, and return to Earth, all on its own, without needing refueling or a separate return vehicle. In one configuration, the vehicle starts in low Earth orbit with a dry mass of 138 tons, carrying 25 tons of payload, 617 tons of methane in its main tanks, and 36.7 tons of methane-oxygen mix reserved for landing. From there, it heads to the Moon and lands, burning about 520 tons of methane from the main tanks. That's around 5,930 meters per second of delta-v. After delivering its payload, it still has enough propellant to perform a 2,700 meters per second burn for the return trip. Once it reaches Earth, it uses aerobraking to slow down and then performs a final powered landing using its sea-level Raptor engines. That changes everything. Instead of throwing away expensive hardware after a single use or relying on complex multi-stage mission architectures, this version of Starship can do the entire mission, Moon and back, and be reused. That's a massive win for sustainability and cost efficiency in spaceflight. Now, despite all the advantages, there are downsides to using nuclear propulsion, especially for a company like SpaceX. First, gaining access to nuclear technology would be a major challenge. SpaceX can't just build a nuclear rocket on its own. It would require direct government support, regulatory clearance, and likely years of collaboration with agencies like the Department of Energy and NASA. Even if they do secure access, testing and developing nuclear propulsion would be a fundamentally different endeavor from anything SpaceX has done before. Their current model thrives on rapid iteration: test, fail, fix, and try again within days. That simply doesn't work with nuclear technology. If a prototype explodes on the stand, it's not just scrap metal. It's a federal investigation and a months-long safety review. The whole move fast and break things philosophy becomes untenable when nuclear material is involved. Every failure becomes a national security event. Then there's the radiation issue. On the ground, nuclear thermal rockets are surprisingly safe. When fueled with low-enriched uranium, they don't emit dangerous radiation before ignition, and they only turn on once they've staged off the super heavy booster, far above the ground. This means launch crews and infrastructure aren't exposed to radiation under normal conditions. Even in the case of a launch failure, the uranium is stable and not immediately hazardous. It's safe enough to touch in solid form. But everything changes after ignition. Once the reactor is active, the fuel becomes intensely radioactive. Even after shutdown, it continues to emit heat and radiation, up to 1% of the reactor's maximum power output. For these engines, that could mean several megawatts of residual energy. While this decays rapidly, the area around the engine remains dangerously radioactive, lethal for days, harmful for weeks. NASA estimates that a nuclear thermal engine doesn't return to a safe state for human interaction for about a month after operation. That delay directly conflicts with SpaceX's goal of rapid reusability. If a nuclear-powered upper stage returns to Earth shortly after delivering its payload, the engine will still be hot. Even if re-entry and landing are handled by chemical Raptor engines, the radioactive upper stage poses a serious challenge. Ground crews would need full radiation protection, Refueling stations would require heavy shielding, and tasks like payload integration or booster restacking would become risky and complex. Honestly, many space exploration challenges, far beyond just rocket propulsion, require a reliable, high-density power source. For a specific class of missions, particularly long-duration operations on the Moon, nuclear power isn't just preferred, it's likely the only viable option. That's why acting NASA Administrator Sean Duffy has called for the development of a nuclear fission reactor, targeted for deployment on the lunar surface by 2030. This reactor will likely serve as the primary power supply for the first US-led moon base, enabling humans to stay on the surface for increasingly extended periods. To support sustainable human exploration, NASA plans to leverage local lunar resources, like extracting water and oxygen for life support and harvesting hydrogen and oxygen as spacecraft fuel. Doing so dramatically reduces the amount of material that must be launched from Earth, significantly cutting costs. One promising source of these resources lies in the Moon's permanently shadowed regions, craters at the lunar north and south poles that never receive sunlight. Scientists believe these regions contain water ice, a critical asset for any long-term human presence on the Moon. NASA's Artemis campaign is specifically targeting the lunar south pole to take advantage of these potential ice deposits.